Hello, I'm Louise. I'm a new PhD student at the Software Languages Lab of the Free University of Brussels, and I'm going to present my master thesis. So, in my master thesis, I created a new language named FLOREnce, which is a combination of functional reactive programming with logic reactive programming. So, what are these paradigms? As we all know, functional reactive programming is a paradigm which uses signals and streams as abstractions to generate a directed acyclic graph to automatically update the state of the program. Here you see two examples of these abstractions in Rescala. It's not important to code, but it's just an illustration. So then you have logic reactive programming. And what is logic reactive programming? Well, it's researched by our lab. And in our lab, it's defined as languages which contain rules to detect patterns in an open world. And these are three PhD theses that discuss this paradigm. So you have Mudra, which is a language to detect gestures in an open world using rules. Then there is Parthenon, which uses rules to detect security vulnerabilities in streams. And then you have Sparrow, which uses rules to detect in a distributed setting patterns, such as home domotica. So in my master thesis, it was the vision to combine these two into one language so that you could do pattern matching and computations in an open world. So if you think about it, adding logic reactive programming to functional reactive programming is actually adding an end to the functional reactive programming paradigm. I know some people will say, my functional reactive programming language has an end, but mostly these are asymmetrical ends which only use one stream. So, and in my language, it would be to use multiple streams. And I will give an example of what I mean by using multiple streams, using this example. So in this example, you have two streams combined by the AND operator. The first stream, the red one, will emit two events. Then a third stream emits a third event unrelated to any of the AND operator. Afterwards, the second stream of the AND operator also emits a stream. So, but now is the question, what will this AND emit? Well, there are three semantics that could occur. The first is nothing will happen, because all the events did not happen at the same time. The second semantics is that the AND operator always stores the last event of each stream and then combines it with each incoming stream. The third semantics is that the AND operator stores everything of each stream and then combines it with each incoming event. This third semantics is what we want. However, the problem is that in an open world, this will give a problem with memory because there could be out of memory errors. And this is solved by logic reactive programming by using constraints on the number of events. So in my thesis, I looked at how to combine these two paradigms, and this resulted in the language FLOREnce. FLOREnce only looks at streams and not at signals. So to explain FLOREnce, I will use an example, namely the fast food example. And in fast food restaurants, you have electronic menu boards on which users click to order food. In this scenario, you both need to compute things such as the total sum of the order, but also detect patterns such as I want to detect a Big Mac pattern because in this case, this gives a reduction, for example. So that's why this is a good scenario, therefore. So this is the layout of a FLOREnce program, and FLOREnce has three big parts. The first part, the model part, is where the developer can define variables. The second part is where the graphical user interface is defined. And the third part is where the programming logic is defined. So how does this work? Well, the graphical user interface will emit the events generated by the interaction with the user to the hidden part of the program. There, it will do its computations, which can include a database to store the events for the end operator. And then it can also use the model variables defined in the model part of the program. And at the end, it will push the values back to the graphical user interface to update it. So that was the overview. And now I will explain the different paradigms in FLOREnce. So I will start with functional reactive programming. And functional reactive programming in FLOREnce is done by using reactors. And reactors will generate a graph as you see there. And how does it do this? Well, first in the input part of the program, there will be parameters defined. And these parameters define the input streams in the program. So for example, you have a button which generates a stream. This parameter will present that. You can optionally also add a parameter for a model variable that can be then later used inside the nodes of the tag. Then you have the body. And in the body, new stream definitions are defined using operators such as or map. And these then create also new nodes at the graph. So all these definitions inside the body can be seen outside of the reactor. So therefore you have the out statement, which allows the developer to publish a stream outside of the reactor. So this then created that graph there. However, this graph does nothing because it's not connected to anything. And therefore you have the deploy statement, and the deploy statement will copy the tag and will connect this tag to the graphical user interface and to the model variables that it needs to compute. And whenever a user interacts with the screen, the events will be emitted and propagated through the graph. However, this does again nothing, because the output stream is not connected to anything, which makes that the state of the program is not updated. So therefore, you have the update operator, which will connect the output stream of the record again to the graphical user interface to update it. So this was the functional part of FLOREnce. Now the logical part of FLOREnce. So the logical part of FLOREnce exists out of rules like this one. And these rules are converted into a graph you see there. And that is actually a REBLS graph, which is an algorithm from the 80s to efficiently detect pattern match facts to a certain pattern. So now I'm going to explain this rule. So this is a rule to detect a menu deal in a fast food restaurant. So first, in the where part, you can define a pattern, and a pattern exists out of multiple event patterns. And because logic events in FLOREnce exist out of an identifier and multiple arguments, you can specify them here, which in this case is a food identifier and 4 arguments. And optionally, you can also add constraints on these arguments, such as here where type burger needs to be of type bacon or of type chicken. And in this case, you have trees of these events that need to occur before the then part is executed. And in the then part, a new event is created, the food menu deal event. And this event is again propagated into the system to check if it triggers any other rules. As you see here, there is a number, and this number is actually a time to live number to indicate how long the event can be in the system, and this is to prevent the out of memory error that I explained earlier, because after this time expired, it's automatically removed by FLOREnce to prevent memory problems. So that was functional and the logical part. And now we wanted to them to interact with each other. However, there is a problem. As you see here, functional reactive programming has events on multiple output streams that are atomic and do not have an identifier. Well, logic reactive programming actually has multiple arguments and does have an identifier. So to actually be able to have them interact with each other, these events need to be converted into events from the other kind. So, and this is done by the operators for all and the collect operator. The for all operators will allow from the logical part to the functional part for events to be propagated, and the collect operators will allow from the functional part to the logical part to be propagated. So, how is this done? Well, the for all operator takes just as in a rule in event pattern, which will detect a certain logical event. This event is then propagated to a reactor. As you see here, 2 reactors are deployed. This is because a logical event can be added to the system, but can also be removed from the system. And in the case of a removal, it will be propagated to a different reactor than in case of an addition. So how is this done? Well, so you first have the logical part which detects an event. This will be propagated to an inter-paradigm node, which will split up the different arguments in the logical event and remove the identifier. These different atomic events will then be put on the different input streams of the necessary reactor. So that was from logical to functional, and now from functional to logical. So in case of reactors, you have output streams, just as with update that can be connected to something. In case of the collect operator, it will be connected to the logical graph. However, there is a problem. So it can be that new item ID emits an event, but the other 3 output streams do not emit an event because they are streams, so they don't always have a value at the same time. And therefore, the collect operator creates a buffer in which the events can be temporarily stored. For example, the first output stream emits an event, but it does not have enough arguments to create a new logical event. So it will store it in a buffer. Then a new event arrives at the first space, at the first output stream. So again, it will be stored in the buffer. But then 3 events are emitted by the 3 other output streams, which then, as you see, then it's full one row in the storage, and this means that a logical event can be created. A logical event needs an identifier and a time to live parameter. So these are defined during the compilation and the collect operator. As you saw, there were two events emitted by one stream. But if another event was emitted before the other 3 events, then the oldest event would be removed from the buffer to prevent out of memory problems. So as I previously said, the reactor and the rules are compiled into a DAG. The FDAG for the functional part, the read graph for the logical part, and is interconnected by inter-paradigm nodes, which result then in a flow DAG, which connects both kinds of DAGs. So to validate this, the fast food restaurant scenario was implemented in both FLOREnce, but also in another language, namely Reactors. And afterwards, the code was split up in 5 categories, and these are the 5 categories. So you have unidirectional dependencies, which are callbacks and deployments, bidirectional dependencies, which is the code necessary to detect the patterns, code logic is to specify the patterns that you want to detect. Computational logic is code to compute things such as reactors, and then insert and delete, which is the code to manage the database. For each category, I look at the number of terminal symbols and number of lines, and this was the result. For unidirectional dependencies, you actually had an increase in number of terminal symbols and lines for FLOREnce compared to Racket. However, when we looked at the code, we saw it was much clearer the dependencies in FLOREnce than in Racket, so we don't see this necessarily as a bad thing. Then you have computational logic, where there was not really a significant difference. And then you had the other three categories, where there was a decrease in number of lines and terminal symbols compared to Racket. And this is because FLOREnce takes care of this by using the logical paradigm. So we find that because of this, we succeeded in our goal to combine these two paradigms. So that was my master thesis, in which I created the language FLOREnce, which combines both logic reactive programming with functional reactive programming. Thank you for your attention.
Thank you for giving much time for question and comment.
Thank you for your talk. Maybe you mentioned it, but what happens if events arrive when the translation from functional to logical and the buffer is full?
Oh yeah. So if a third event would arrive from this, I will go back one more slide. So if a third event would arrive from this stream, then the oldest event is removed from the buffer and another event is added to the stream. So this one would be moved up one place and the other would be put in his place.
I see. Is there a downside to doing this? Like, are you losing information or is it just fine?
I think it depends on what kind of application you want to implement. So if it's really important that you have this information, then it is indeed a downside. But you have multiple actually collect operators. So you also have a storage where you have 3 rows and a storage where you have 4 rows. So there you can then actually try to take a bigger kind of storage. But yeah, it could be if the storage is not big enough that there is information loss.
Okay, thank you.
So, any other question or comments?
I don't know. So, if you do the translation from logical to functional and then back to logical, is it do you lose anything or is it completely preserved?
Well, it depends what you describe as losable, because if you, for example, you create a new string, a new event. So in that event, you can have information that is different than in the original events. That then can be triggered. That then can trigger actually the for all operators. So, but if you go directly from functional to logical to functional, and in case there are no in case that the collect operator is not initiated by other streams at the moment, then yeah, there is no loss of information.
Okay, thank you.
Okay, any other question? So I have one question. So have you ever checked So have you ever checked compared with let's say another paradigm, so, constraint programming or constraint logic programming things, the relationship to constraint logic programming? Yeah, that's a bidirectional, let's say, constraint.
We didn't really look at constraints in the logical part, but that could be a, um, a thing for in the future.
Is there any other question? No? No? This one. Okay. Thank you, Hoshi. Thank you very much.